Hi everyone, this is a video introduction to area functions. If you already know about this connection between the area and antiderivative, it is important that you forget about that at the moment and pay attention to its logical development toward it. It is called the fundamental theorem of calculus that connects these two, and this area function, it is something, that theoretical concept we need to consider to properly introduce this fundamental theorem of calculus. So area, its concept, is defined as a definite integral. The very motivation of a definite integral is to define the area of a region. The way we do that is, first, we consider something called the Riemann sum. It's Riemann's idea to properly define the area of a region bounded by a curve using this Riemann sum. So there are various different Riemann sums they're all supposed to converge the same number, and that is the very definition of a definite integral. And by looking at this definite integral, this area function is something one can consider, and that is important connection to something called an antiderivative, and therefore establishing a connection to the antiderivative as well. Now let's take a look at this example. The function we're looking at, this f of x, is e to the negative x squared times cosine of 3x. And we're considering this definite integral and called the area functions. This is the value of definite integral. This base value a is to be fixed to be -1 in this entire discussion. That a value never changes, always -1. And this x value is the main variable of this function called area function, and the following is the algorithm of f of x. It is a key to understand that you accept this as an algorithm, not as a formula. In mathematics, functions are defined as an algorithm or concept rather than just a simple formula. That is an example of a function, but function is a bigger notion. So given an input x, whatever that is, let's say in between these domain or numbers we're looking at, -2 to +3, anything you're given, and the following is the algorithm. You place that input number up here as an upper limit of an integral and consider this definite integral and think about the value of the definite integral. Actually computing this definite integral sometimes is impossible in an exact way, so we can only think about it as an approximate value, such as some Riemann sum, not the limit of a Riemann sum. So given value of x, put that number in the upper limit of this integral and think about this, the value of definite integral. Here, if your x value is 0, you will put that x value 0 here, and the meaning of this definite integral, starting from -1 to 0 of the definite integral, will be the signed area from starting from -1 up to 0. So this is negative region. Seems like slightly bigger positive regions are there. Altogether, for this x value 0 here, it turns out the value is 0.1825. So again, the algorithm is that giving an x value, consider this definite integral where x is an upper limit, and that is the output. So as we change this x value, and we will change this upper limit, therefore we'll end up at different output value, which is the definite integral value. Usually definite integral is introduced as a number, but as we vary one of the limit up there, especially the upper limit, we have a functional relation. So I'm going to vary this x value starting from 0 to the different value. As you can see, if I put x value somewhere over here, which is roughly 0.52, the area all the way from -1 to up to there turns out to be 0.4894. So I hope you see this functional relation. As you change this right endpoint, the signed area of this changing as well. That's the functional relation. Whenever there's a relation is understood, mathematicians say the function is defined. The next thing that people do after the function is defined is to understand the function a little bit more. Either you come up with the formula of that function, or you think about the graph of that function. Those two things are the standard thing to represent the function. Here, finding the formula of this particular setting is almost impossible, so I will use the graph of this function in here. So what I'm about to do is a given x value, such as 0.14 in here, we're going to look at this output value, not that one. That would be the output value of f of x. We're looking at this new function called the area function, whose input is 0.14, output is 0.3. So for that input, I'd like to plot that 0.3 somewhere here. That will be somewhere at that location right there. So if I repeat that with the various different x values here and there, and put that whenever this x value is 0.2, I'm going to put the 0.2 over there, and it'll be the graph of the function of capital F of x. Before I show you the picture, I'll discuss a little bit about what happens starting from the very negative one in here. What happened to this function value f of x? So if x is -1 here, I didn't get to the -1, let's say it's almost -1, then it's easy to calculate. You start from -1 and ending up at -1, so therefore it's supposed to be 0. Since it's not precisely -1, we're looking at a number that is very close to 0 but not exactly 0. But if it is perfectly -1, you know it starts from -1, ending up at -1. The definite integral is supposed to be precisely 0. So the function value f of 0 is 0. That's all I'm saying. Therefore, at -1, you should plot 0 in here. As I change that x value slightly to the right, we'll begin to pick up some of the region, but because it's below the x-axis, this is a negative number. So we have a negative number assigned. So for that value, let's say it's roughly negative 0.7, we have to plot somewhere down there. Alright, as I go up to this particular point, which is interesting, from there we begin to pick up positive region. And all the way up here, there's the region up to there is a 0.144. So we keep picking up negative number, picking a negative number in here, and as I change that x value, I pick up more negative value there. Alright, but as soon as I pass that point right there, I begin to pick up positive value. So up to your negative value and begin to add positive value, so that you can see that it's growing, it's going up. So if I go all the way up to here, picking up and more positive region all the way up there. So I added this much of a region, now it's bigger, so I eventually get this positive number. As I pass that point, it's not decreasing. The function of f of x, little f of x, is decreasing, but as an area, as I go to the right, I'm still picking up the positive regions. So compared to what happened when this blue bar is over here and over there, is that when the blue bar is over here, we're picking up the region a lot more and bigger region. But at this point, as you go right, I picked up this much of a region. Compared to the next one in there, I picked up much smaller region. So you can say, and here capital F of x is increasing fast, and after that point, capital F of x is increasing slow, not decreasing. What is decreasing in here is little f of x, but as capital F of x picks up still positive region, it's still increasing, but it's increasing slower than it was over here. So that's what's going on in between this one and there. So when it reaches this point right there, it's done with it picking up positive regions, and it begins to pick up negative region down there. So from that point on, as you can see, before it keeps increasing, now it's 0.489. As soon as you pass that, it begins to decrease as it picks up negative regions. So as I click this one, it's going to show you the graph of this capital F of x, and that'll visualize this area function and give a little existence to that. It did not work. Now it's showing. So as I said before, when x is -1 here, the capital F of x must be negative value there. Alright, it's back again. When the function is in between, x value is in between here and here, the capital F of x value is increasing rapidly. As soon as the x value passes that point, the increasing and slow down, which is represented as a concave down. But as soon as you pass that point right here, it begins to decrease, so it's decreasing like that. So again, computing the formula of capital F of x is nearly impossible, but we can still represent this area function in this way using the graph. So here's a summary of what we did. We started with the function, and we considered definite integrals, where we fix the lower bound but play with the upper bound. It creates some function, it's called area function. We denote it with capital F of x. It is known as fundamental theorem of calculus that makes a connection to this area function. We give an existence to this area function, and it turns out to be, it has a property of that its derivative is equal to f of x. So there's an entrance of antiderivative. But before we think about this antiderivative, there's this notion of area function that bridges this two, and that's the logical order of things that are happening inside the fundamental theorem of calculus. So finally, this makes a connection between definite integral, which is about the area, and its concept does not involve any antiderivatives, but fundamental theorem calculus says that it is really connected to antiderivative. So that's the role of area function inside this theory of a fundamental theorem of calculus. Alright, thank you for watching the video.